Welcome back to track 1, implementations and use cases beyond mobile. Our next presentation is mobile user interface aggregation for heterogeneous compute intensive solutions, and there will be a quiz just on the title alone. Abdullah Raouf of Lattice. Abdullah Raouf is a senior product marketing manager for Lattice, focused on FPGA and ASP solutions for the mobile markets. He has more than a decade of experience in semiconductor product management, and he holds a Bachelor of Science degree in electrical engineering from UC Davis and an MBA from Santa Clara University. Abdullah.
Thank you. Thank you, everybody. So yes, the title is, as was read earlier, Mobile User Interface Aggregation for Heterogeneous Compute Intensive Solutions. Say that 3 times fast. That was not my choice of title. My title is 2 words, and I'm going to share you those 2 words, and that's going to be the basis of the entire presentation. Carpe diem. Seize the data. Take advantage of the data. There's data being captured all around us. Cell phones, wearables, watches, clothes, shirts, shoes. The lights around you are taking your picture sometimes. There's data being sensed all around you, so you need to make most use of that data. You need to transfer that data correctly using some great interfaces available by MIPI. And you need to process that data, analyze that data, and I'm going to talk about some of that analysis in today's presentation. So remember, the title is Carpe Diem, all right? Not this long thing. All right, so the agenda. I'm going to talk about capturing data, as I mentioned, what sensors are around you, what sensors are important for different use cases. And then I'm going to talk about how do you transfer the data once it is captured. Which MIPI standard should you use? Why are those MIPI standards better than other standards on the market? And then I'm going to talk specifically in more detail about the data analysis. The first 2 sections within the presentation are going to go by quickly. And that's because there's a lot of other people training you on those sections. What is MIPI? What are the data transfer rates? What are the different types of standards available? A lot of training happened on that. So I'm going to focus more on the analysis part, mobile heterogeneous computing part, trying to explain what are the different architectures available for you to analyze these data. And I'm going to talk specifically on why FPGAs are good and optimal for analyzing this data. So first off, what's sensing information? Everything. A lot of stuff around you is always on and always sensing data. Like I said, there's lights on the street that are just sensing, listening for voices, listening for car crashes, reporting those car crashes. If there's a light or some kind of fixture outside of a bar, if a fight happens, though there's situations out there where reports can be filed instantly, all automatic. Your watches are tracking where are you, what are you looking at, what are you doing, are you running, walking. All of this is capturing data, and it's on all the time. So the critical thing is a lot of these products that are shown on this slide are battery powered. So this always on functionality has to be done in such a way where you don't consume that much power. So I'm going to talk about how do you make sure you have a more energy efficient solution as we go through these different steps and these different use cases. So what are the type of sensors you'll find? You'll find image sensors. They're used for gesture recognition, eye tracking, proximity detection, depth detection. Let's say you're driving in a car and you have an image sensor trying to make sure you don't crash and hit something. That's making sure the depth between you and the car in front of you is at a certain distance. And if you start getting closer to that distance or shortening that distance, something's going to happen. Your brakes are going to start, and it needs to happen quickly. So you can't rely on processors that are slow and that react too slowly. Health sensors, making sure your health is up to date, your EKG, EMG, EEG, all of the different elements within your body are working correctly. Audio sensors, speaking. A lot of people are now speaking to their machines. In fact, people have friends called Siri, called Alexa, and they communicate with these electronic devices. And I'm going to show you kind of some more in-depth use cases on that coming up. So bottom line, sensors are everywhere. And now the problem is a lot of these sensors have different interfaces. So this slide just shows you all the different interfaces. I don't want you to memorize what these interfaces are, but trust me, there's tons of interfaces available. So how are you going to easily aggregate these sensors into a single processor so that the processor can analyze that data? Well, one approach is to use some kind of FPGA which can aggregate all the different interfaces that I showed you on the previous slide, and it can aggregate it over a single bus. And depending on how many interfaces you have is going to determine which type of solution you're going to use. On the bottom of the slide, you can see different size solutions that are available on the market. Depending on how many IOs you need, depending on how many interface solutions you need. And what is that interface to the SoC? Well, it's going to be your MIPI interface. And it depends. If you want to transfer audio, you're going to choose your Slim Bus or SoundWire interface. If you're going to transfer some kind of camera image sensor, you're going to choose your CSI. So there's different types of MIPI interfaces for different types of image sensors, or type of sensors in general. So this slide shows kind of the MIPI standard that's more ideal to the different use cases. Again, I don't want to go through in detail on these specific MIPI standards. There's training all around today and as well tomorrow on what these standards do. What I'm going to focus on is starting on the next slide. Analyzing the data. So now you've captured the data, you've transferred the data, and now you want to analyze the data. So there's a lot of different use cases. The one I mentioned earlier is voice recognition. So you can communicate with your devices. You can start talking. Like I said, there's people that have friends named Alexa, Siri. So if you want to communicate with your device, you could say something very simple, like, hey, Lexi, wake up. Right? You can say something very, very simple like that, where on all of a sudden your device is going to wake up and it will be able to start communicating with you. You can also have facial recognition. So let's say you're sitting on the beach and you want to have a meeting with your colleagues, but you don't want your colleagues to know you're on the beach. Right? So you sit on the beach, all your background clutter is completely removed because there's maybe some kind of algorithm that's determining what's clutter and what's not clutter. So let me get back to the voice real quick. So let's say you want to communicate. Let's say, hey, Lexi, wake up. I have a question to ask you. So let me try that again. Hey, Lexi, wake up. I have a question to ask you. All right, never mind. So you're sitting at the beach and you don't want your coworkers to understand that you're at the beach. So you remove your background clutter. It detects who you are, so it has your name on the top of the screen so you can know who you are. Now you can have a full live meeting, and all of this is done with algorithms. And here's a list of kind of the different algorithms that are available in your everyday life. So in a car, you want to make sure that you don't run into something in front of you. We talked about that earlier. You want to make sure that there is security, surveillance going on all the time to making sure that if an accident happens, if a robbery happens, so something is out of place, something is not in the norm, so you have pattern recognition algorithms. All of these algorithms can be implemented in two ways. This slide shows the two methods. One is using traditional algorithms. These are based on preconceived events. So you have an equation, you want to compute the exact equation, you know what the outcome is going to be. That's kind of what you use now. I'll give you an example. Let's say distance formula. It's a fixed number. You just want to compute how far two items are from each other. So you have a specific formula and you compute the distance. But let's say you want to predict something. You want to have a probability of something. The probability of two items hitting each other. That's going to be more of handled in neural networks. So neural networks basically finds patterns in data. So you have tons and tons of data coming in, and these data are in the form of events. When something happens. And you want to predict when something else similar will happen at the exact same rate or something like that. So that's going to be implemented in neural networks. Neural networks are ideal integrated in GPUs, DSPs, or FPGAs, whereas traditional algorithms have been implemented in software only, so processed in the cloud most of the time. Okay, so keep that in mind. So now, basic neural networks use these multiply and accumulate type building blocks. So they each have these multiply and accumulate building blocks to compute. And they have to compute probably 1,000 times, 1,000,000 times, continuously repetitive computation, and they have to do it very quickly. And they have to do this really quickly to find that probability. So the difference between using a neural network in a GPU versus using a neural network in an FPGA, there's one simple difference. Inside of a GPU, same thing. You have the neurons, you have the multiply and accumulate, but you do it in series, so one at a time. So it takes time. So if you want to react very quickly, what do? You speed up the clock very quick, very fast, which means your power consumption goes up significantly. If you want to do it in FPGA, you could do the whole entire computation in parallel, all at once. And if you do it all at once, you can reduce your clock speed because you could do it all in one cycle. And you guys know that the faster your clock speed goes in a processor, the more power you're going to consume. So an FPGA is going to be the lowest power option for doing this. So mobile heterogeneous computing, what is it? There's different types of solutions out there trying to offer support for heterogeneous computing. There's your single core processor, which 10, 20 years old, maybe 30 years old. And then people started getting into multi-core, your quad core, your octal core. And then there's a heterogeneous processor. That's your graphics processor, your GPU, that has DSPs built in, your ARM processor or your x86 processor built in. And then you get to your FPGA. So as you go to the right on this table, the further right you go, the more quicker your repetitive computation becomes. I showed you that in FPGA you can do tons of repetitive computation all in parallel. That's why FPGA is the farthest to the right. Also, some of the values that you can't really see in that blue table of an FPGA versus the other processors are, well, if you have a new idea, a new algorithm, and you want to implement in a hardware solution, you can either wait and spin a new ASIC and get a new heterogeneous processor. It could take 18 months. Or you can simply write new RTL code and insert it into the FPGA, and you have a new solution in about a month. So that's one of the best advantages of an FPGA, very, very quick time to market. It also gives you much more flexible IOs. Your IOs can be different. Let's say you understand the processing that you want to do, but you don't know which MIPI standard you want to use, or maybe another IO. Or maybe you got a new image sensor that doesn't have the IOs that you had anticipated for before. With an FPGA, you could reprogram your IOs instantly, and you can have interface directly to those new IO standards. And third is the accelerations available with FPGA. So FPGAs now allow you to have processors built in. So that means if a processor is built in an FPGA, it's actually performance-wise is the same as your heterogeneous processor. But the FPGA gives you one thing that the heterogeneous processor doesn't, and that's the accelerators using the FPGA fabric. So you can actually accelerate portions of your C code so that you can improve the compute capability or the compute time. So now, this slide was all about compute time. The next slide I'm going to talk about power consumption. So this is data not from me, it's from 4 different sources. NVIDIA released some information, UCLA, Microsoft, and a university in China. All these 4 different sources released information on power consumption comparison with GPUs versus CPUs, with CPUs versus FPGAs, and with GPUs versus FPGAs. And you can see the higher the bar, the more power efficient. The green bar is FPGAs, and you can see in every single one of these plots, the green bar is always the highest. That means the FPGA is always the most power efficient. So the quickest repetitive computation element, the most power efficient element is FPGA. So if you want to do the neural networks, your solution will be an FPGA. So what are some FPGAs that are on the market? On the bottom, it shows you the package size. Now FPGAs are thought of or perceived to be very large devices. 28 by 28 millimeters, 40 by, is huge devices. That's not correct. We have 1.4 millimeter FPGAs on the market. They have very few IOs, only about 10 IOs, but sometimes that's all you need. Maybe you have a couple of PDM microphones and you want to merge it for some beamforming, and that's all you want to do. You don't need that many IOs. So the range of FPGAs that are shown on this slide tell you kind of what you want to support. If you want to support simple functions all the way to machine vision, using the MIPI DeFi, running at 4K video resolutions and analyzing 4K frames all at the same time, you're going to want a slightly larger FPGA. So this slide just shows some of the different FPGAs that are available. So I'm getting a thumbs up. They want to do the demo again. So let's try before I get to my summary slide. All right. So sometimes you interact with your device. I tried earlier. And you ask it questions like, hey, Lexi, wake up, I have a question to ask you.
How can I help you, Abdullah?
There's so many people in this audience. I'm surprised that you were able to determine that I was the one speaking. How did you do that, Lexi?
I can determine who is speaking to me by using a pattern recognition algorithm implemented by Lattice's mobile heterogeneous computing solution, which is offered in their FPGA products.
So I already described to you guys what mobile heterogeneous computing is. So I don't know if I should ask again, but let me just ask, what is mobile heterogeneous computing, Lexi?
MHC is parallel processing using dissimilar processing elements for repetitive computation in an energy-efficient manner.
You got that? All right, so let me summarize. So FPGAs are changing the way you interact with your device. You can talk to it. You can make gestures, and it'll determine what gesture you're making. It'll determine who's talking using pattern recognition for facial recognition. It's energy efficient, allows you to do parallel processing. It has memory embedded, so you can actually buffer the sense data. So if you want to do some low-level processing in the FPGA and then do the higher-level processing in the cloud, FPGAs allow you to do that. It supports the most flexible IOs, and the key to FPGAs is the acceleration of your innovation. You have an innovative idea, you don't have to wait for an ASIC. You can implement it in a month within an FPGA. And the overall theme of the slides was not the title of the slide, it was what? Carpe Datum. Seize the data, make most use of the data, understand how to capture the data, how to transfer the data, and how to analyze the data properly. So that's it. Any questions?
Thanks. So you showed in there earlier that it's more energy efficient within FPGA to do the parallel processing. Can you give us roughly what's the benefit that you would see over a processor?
So it depends on the use case. I'll give you an example that which we use as a benchmark, audio processing, phrase detection. So we took some processors off the market and we compared to our FPGAs. We're about a third the power. So 60% power reduction using an FPGA with a parallel processing functionality.
Thanks.
Yeah. Any other questions?
Lexi, do we have any other questions?
Why?
All right, guys, thank you very much.
Very good.